You can see clearly there is a clock here. So there is a clock here. So these are the positives triggering clock. So this is called as the time period of the clock or T clock. Then see here basically there is a strobe signal. So strobe signal we are going to give here in this format. So you can see really I am going to give a strobe signal in this format. So in a one clock time period, so the previous called as the NTPD-FF and this is called as the TS. So you can see clearly, so T clock should be always greater than or equal to N into TPD-FF plus TS. So n small n is called as the number of flip-flop used in the asynchronous ripple counter. Small n is called as the always the number of flip-flop used in the asynchronous ripple counter. Because I have already told you for asynchronous only T clock is always greater than or equal to N into TPD-FF. Whereas for the synchronous counters, ripple counters, for synchronous ripple counters, then we are going to get T clock is equal to greater than or equal to TPD-FF only. So therefore for here ripple counter we will use the N here. Whereas for we can say, see finally I can say listen carefully, T clock is always greater than or equal to N into TPD-FF for asynchronous ripple counter, whereas for T clock is always greater than or equal to TPD-FF for synchronous ripple counters. So these things that you always need to keep in your mind. The small n is called as the number of flip-flop used in the asynchronous ripple counter, and TS is called as the output is stable in this interval. So output is stable only in this interval, and here the output is not at all stable, or we can say it is not in a stable region. So TS is the output here is stable in this interval. So output is stable in this interval, and N into TPD-FF is called as the in this time period output is in the transient state. So in order we must not see we use this strobe signal low in this period of NTPD-FF. So I already told you there is always a transient state. There is always a transient state in the asynchronous ripple counter. So if you don't want to see it, then definitely you have to make the strobe signal as low in the time period, which is N into TPD-FF. So therefore you are not able to see that one. So this is a very important concept that you always have to keep in your mind. So T clock is always greater than or equal to N into TPD-FF plus TS. So small n is called the number of flip-flops which are used in the synchronous ripple counter, and TS is called as the output is stable in this interval. So TS is called as the in this time the output is always stable in this interval, and N into TPD-FF is called as the in this time period output is in the transient state. So in this time period output is always in the transient state. So in order we must not see we use this strobe signal low in this period of NTPD-FF. So in this time period, so in this time interval, output is in the transient state. So we must not see. So in order we must not see, we use this strobe signal low in this period of NTPD-FF. So I already told you, see, output is always stable in this region, but output is not at all stable. It is always in the transient state. So we don't want to see this transient state. So that is the reason we have used the strobe signal as low here. So listen carefully. We have used the strobe signal as low in this period because we don't want to see the transient state. Whereas in this case, the output is stable here. So therefore, T clock is always greater than or equal to N into TPD-FF plus TS. So small n is called the number of flip-flops used in the asynchronous ripple counter, and TS is called as the and in this time interval the output is always stable. Whereas TPD-FF is called as in this time interval or in this time period output is in the transient state. So in order we must not see we use this strobe signal low in this period of NTPD-FF. So in this time period output is in the transient state. So in order we must not see we use this strobe signal low in this period of NTPD-FF. So therefore in this time interval the output is in the transient state. So in order we must not see we use the strobe signal low in this NTPD-FF. So finally I can say that so this is the clock interval time period, and this is the strobe signal which is a period which is NTPD-FF and TS. So T clock is always greater than or equal to N into TPD-FF plus TS. So in this TS, we can say output is always in a stable region, whereas here a small n is called the number of flip-flops used in the synchronous ripple counter, whereas here always in this time interval, which is NTPD-FF, always output is in the metastate, or we can say output is always in the transient state. So in order we must not see, we are going to keep the strobe signal as low in this range. In ripple counters, transition state will present due to propagation delay. Due to this decoding errors will present and to avoid decoding or translation errors, strobe signal control is used with the pulse width of TS. These things I've already told you in ripple counters especially. So in ripple counters, transition state will present due to propagation delay. So due to this, decoding errors will present, and to avoid decoding or transition errors, strobe signal control is used with pulse width TS. And what I told you, some may think that this transition state is also stable state. They are going to think like that. So that is the reason we must not see that state. So because of that, we are going to the strobe signal in the width of TS, and the remaining time we are going to make it as 0. So this is a very important point that you always have to keep in your mind. Because if you are going to see the transition state also, people may think that it is also a stable state. So in order to make them not to confuse, we are going to the strobe signal of pulse width on the TS. There the output is stable, whereas for the remaining time period it is low, because there we are going to see the transient state. So now if you are going to keep the strobe signal 0, people are not able to see the transient state also. So like this we are going to do this one. So in ripple counters means either it is a synchronous counter or either it is a asynchronous counter. Ripple counters means these are either synchronous counter or either these are the asynchronous counters. So in ripple counters, transition state will present due to propagation delay. So in ripple counters, transition state will present due to propagation delay. Due to this, decoding errors will present, and to avoid decoding or transition errors, strobe signal control is used with the pulse width TS. So this is an important point that you always have to keep in your mind for your lifetime. So therefore, in ripple counters, transition state will present due to propagation delay. Due to this, decoding errors will present, and to avoid decoding or transition errors, strobe signal control is used with the pulse width TS. So in the ripple counters, always the transition state is going to get present. So people may think that it is also stable state. So these transition states are going to present because of the propagation delay. So in order to remove this one, we are going to make the strobe signal as 0 for a certain amount of time, which is N into TPDFF, and for the remaining time we are going to make it as add 2, because in the time the output is always in the stable state. So like this, that you always have to keep in your mind. So finally I can say in ripple counters, either it is a synchronous counter or it is a asynchronous counter, always transition state will present due to propagation delay. So due to this, decoding errors will present, and to avoid decoding or transition errors, strobe signal control is used the pulse with TS. See, if A XNOR B is equal to C, then B XNOR C is equal to A, and A XNOR C is equal to B, and A XNOR B XNOR C is always equal to 0. So this is a very important point that you always have to keep in your mind. Suppose if A XNOR B is equal to C, then B XNOR C is always equal to A, and A XNOR C is always equal to B. So therefore A XNOR B XNOR C is always equal to 0. So this is an important point. Suppose if this is the condition, then we are going to get all these crazy things we are going to get. So if A XNOR B is equal to C, then B XNOR C is equal to A, C XNOR A is equal to B, or A XNOR B XNOR C is equal to 0. So if always if A XNOR B is equal to C, then definitely B XNOR C is equal to A, C XNOR A is equal to B, and also A XNOR B XNOR C is equal to 0. This you can easily check with the help of this condition. So you can say clearly, if A and C are true, means A into C. If B and C are false, means B bar C bar. If A, B, C are true, means A, B, C. If A, B, C are false, means A bar, B bar, C bar. So these are the conditions that you always have to keep in your mind. So we can say, if A and C are true, means A into C. If B and C are false, means B bar, C bar. If A, B, C are true, means A, B, C. If A, B, C are false, means A bar, B bar, C bar. So this is the convention that you always have to keep in your mind. If A and C are true, means A, C. If B and C are false, means B bar, C bar. If A, B, C are true, means A, B, C. If A, B, C are false, means A bar, B bar, C bar. So these things that you always have to keep in your mind for your lifetime. True means keep as it is. False means keep the bar of that one. So and means always go for the into. So listen, true means always keep as it is. False means keep complement of the our letter, and means keep the dot. So this is a concept that you always have to keep in your mind. So A and C are true means AC, B and C are false means B bar, C bar. A, B, C are true means A into B into C, and A, B, C are false means A bar, B bar, C bar. So true means keep as it is, that it is. False means keep the complement for the letters, and means you have to keep it a AND symbol, or you can say AND symbol means not symbol you have to keep here. To an stable multivibrator circuit, if we add any extra buffer or inverter or both, then the net circuit is still a stable multivibrator, and time period of the output square waveform depends only on the odd number of inverters inside the feedback. So I already told you, in a stable multivibrator circuit, if we add any extra buffer or inverter or both, then the net circuit is still a stable multivibrator, and time period of the output square wave depends only on the odd number of inverters inside the feedback. So this is a very important point that you always have to keep in your mind. So to an unstable multivibrator, if we add any extra buffer or inverter or both, then the net circuit is still a stable multivibrator, and time period of the output square wave depends only on the odd number of inverters inside the feedback. So what I am trying to tell you, suppose I have already told you for an unstable multivibrator, the number of inverters inside the feedback are always odd. Suppose if you are going to add some extra buffers or extra inverters, and if you count the overall inverters, means in a feedback I already told you there are some buffers, there are also some inverters. So if you add all the inverters, if it is odd, then definitely it is said to be a stable multivibrator, and the time period is nothing but 2 into n into TPDFF, where n is the number of inverters. N is only number of inverters which are odd number. You have to consider only the inverters but not the buffers. We should not count the buffers. We have to count only the we can say inverters. So finally I can say that to an stable multivibrator circuit, if you add any extra buffer or inverters or both, and the net circuit is also a stable multivibrator, and time period of the output square wave depends only on the odd number of inverters inside the feedback. So suppose if in a given feedback, if there are odd number of inverters, so extra I am adding some basically I am adding extra some buffers and also inverters. If you count the overall inverters in the feedback, if it is odd, that is going to act like a stable multivibrator, and the overall time period of the square wave output is equal to 2 into n into TPDFF, where n is called the number of inverters, the number of odd inverters. Always the number of inverters means it's always odd number inside the feedback. You must not consider the buffers. The procedure to introduce the time delay in output is to draw the ideal output waveform and then shift it by TPD right shift. I already told you the actual procedure to draw the time delay in output is to draw the ideal output waveform and then shift it by TPD, which is a right shift. I already told you, suppose if you want to draw what is the delay in the output, first you have to draw what is the ideal output waveform, and then you have to shift the signal by right side by a small amount of TPD. We consider propagation delay of the circuit. Then we are going to get the actual output. First you have to draw what is the ideal waveform, and if you want the actual waveform, just to give a shift to the waveform by right side by TPD. So the procedure to draw the time delay in output is to draw the ideal output waveform and then shift it by TPD, the right shift. I already told you one important point, First thing is that you always have to draw the ideal output waveform, and if you want to introduce a delay in output, then you have to shift the output waveform by small amount of time delay by right shift by TPD. Then you are going to get the actual waveform. It is going to include the time delay. So first you have to draw the ideal waveform, and then you have to give a shift to the waveform by right side by right shift by TPD. Then you are going to get the actual waveform. So first you have to draw the ideal waveform, and you have to give a right shift by TPD. Then you are going to get the actual waveform. So we can say that the procedure to introduce the time delay in output is to draw the ideal output waveform and then shift it by TPD, the right shift. Two circuits are equal only if the truth tables are perfectly equal. I already told you. So two circuits are equal only if their truth tables for the corresponding input combinations is same. So for the corresponding input combinations, if the truth table is always same, so we can say two circuits are said to be identical if their truth tables are identical. So we can say two circuits are equal if their truth tables are perfectly equal. Then only we can say they are said to be, we can say, identical. So we can replace one circuit by the other circuit because two circuits are always equal. So two circuits are equal only if the truth tables are perfectly equal. NAND gate and NOR gate always follows the commutative law but not associative law. I already told you all the basic gates, NOT gate, AND gate, OR gate, always satisfies the commutative law and also associative law, whereas the NAND gate and NOR gate are universal gates. They only satisfy the commutative law but not the associative law. So NAND gates and NOR gates, they only satisfy the commutative law but not the associative law. So NAND gates and NOR gates follows only the commutative law but not the associative law. NOR gate is equivalent to bubble AND gate. I already told you NOR gate is always equal to bubble AND gate. So these things I have already explained. So NOR gate is always equal to bubble AND gate. So bubble AND gate is nothing but simply we can say double AND gate. So NOR gate is always equal to bubble AND gate. You can see clearly from this picture. See, I have already told you this is called as the NOR gate. So this is the NOR gate. A, B, and this is NOR gate. Output is A plus B whole bar is equal to A bar into B bar. So this is equal to bubble AND gate. Bubble AND gate means this is the figure. So we have to keep in like NOR gates in between the inputs and this AND gate. So it is equivalent to this NOR gates between them. So therefore now this is A, this is B. So A bar, B bar. So A bar into B bar. So both are same. So finally I can say that NOR gate is equivalent to bubbled AND gate. So NOR gate is equivalent to bubbled AND gate. So therefore NOR gate is equivalent to bubbled AND gate. So this is the concept behind this one. So now if A XOR B is equal to C, then A XOR C is equal to B, B XOR C is equal to A, and A XOR B XOR C is equal to 0. These things I have already told you. Similarly, same concept with the XNOR also. XNOR and XOR both are the same property. Just now we have seen if A XOR B is equal to C, then B XOR C is equal to A, and C XOR A is equal to B. So therefore A XOR B XOR C is equal to 0. Same thing for XNOR also. If A XNOR B is equal to C, then B XNOR C is equal to A, and A XNOR C is equal to B. So therefore A XNOR B XNOR C is equal to 0. So these things that you always have to keep in your mind. If A XOR B is equal to C, then B XOR C is equal to A, and C XOR A is equal to B. So therefore A XOR B XOR C is equal to 0. Similarly, if A XNOR B is equal to C, then B XNOR C is equal to A, and C XNOR A is equal to B. So therefore A XNOR B XNOR C is equal to 0. These things just now we have seen. So odd function is also called as the XOR gate because when the number of input have odd number of ones, then only output is 1. These things I have already told you. So what is the meaning of odd function? Odd function is also called as the XOR gate because whenever the number of input have odd number of ones, then only output is 1. These things I have already told you. Odd function means it is basically an XOR gate because for an XOR gate, for odd number of ones only the output is equal to 1, but not the other case. So finally I can say that only for odd number of ones we are going to get the output as 1, and for the remaining cases we are going to get 0. So odd function is also called as the XOR gate. So odd function is also called as XOR gate because when the number of input have odd number of ones, then only output is always equal to 1. So we can say odd function is also called as XOR gate because if the number of input ones are odd in nature, then only output is always equal to 1. So this is the thing that you always have to keep in your mind. So odd function is also called as XOR gate because when the number of input have odd number of ones, then only output is 1. So we can say odd function is also called as XOR gate because when the number of input have odd number of ones, then only output is 1. So therefore, simply we can say odd function means it is also called as XOR gate because whenever the inputs have a odd number of ones, then only output is always equal to 1. Otherwise, in the remaining cases output is always equal to 0. So now listen carefully. The synchronous counter designed for any count. I have already told you an important point. With the help of a synchronous counter, you can design only the up counter and down counter. But with the help of asynchronous, we can design all the up counter, down counter, and also any sequence of random states, random sequence. So with the help of asynchronous, you can only design the up counter and down counter. But with the help of synchronous, you can design up counter, down counter, and also any random sequence. So now we will see what is the design procedure for the synchronous counter. So synchronous counter designed for any count. First thing that you have to write the previous state and then next state, and then you have to write inputs required to get the next state. So finally you have to make a table. I already told you first table is always previous state. Then you have to keep the excitation inputs to make the output. So these excitation inputs are required to change the previous output to next output. So what are these excitation inputs required to change the output from this previous state to next state? So you have to draw a table like this: previous state, inputs required to get the next state, and this is the next state. So now excitation inputs in a function of the previous states you have to write. So based on this, try to figure out the excitation inputs from the previous state to next state, and then write the excitation inputs as a function of the previous states. And now you are going to get with the help of simplification, with the help of K-map, you are going to get certain expressions, and now draw the circuit diagram. So now try to draw the circuit diagram with the help of these things. So for understanding purpose, so present state, excitation state, or next state. So this is the thing that you always simple keep. So always draw a table of previous state, excitation state, and the next state. So now see, from previous state to next state, then what is the excitation states are required? Just try to figure out this one. These excitation state inputs, what are the excitation state inputs are required? Then try to figure out from present state to next state. Then now try to draw the K-map with respect to this excitation states and the present states. So try to figure out this output and input relation. So now with the help of K-map, try to do the simplification, and you are going to get certain expression, and now you can draw the circuit diagram. So always draw a table of present state, excitation state inputs, and the next state, and try to figure out the excitation state inputs required to change the present state to previous state outputs. Then try to draw the output and input relations like excitation inputs in terms of the function of previous states. And now with the help of K-map, try to do the simplification as simple as possible, and now based on this, draw the circuit diagram. So this is the procedure for synchronous counter of any sequence. So draw a table of previous state and the inputs required to get the next state, and the you can say again next state. So if you draw this one, try to figure out the inputs required to get the next state, or called as excitation inputs. Try to figure out in terms of the previous states. So excitation inputs in terms of previous states, and with the help of K-map, try to more simplification or draw the circuit diagram. I already told you, first thing that you are going to get is VLSI state machine, and then you are going to get the Moore state machine. I already told you because E is going to come earlier than Moore, always VL is going to come earlier than Moore. So in a Moore state machine, output depends on current state of the sequential circuit and external inputs. So in a Moore state machine, output depends upon the current state of the sequential circuit and the external inputs. Whereas in a Moore state machine, output depends on only current or present state of the counter. So these things I already told you, very important things. See, always in a Moore state machine. So in a Moore state machine, the output depends on current state of the sequential circuit and also external input. So therefore simply we can say very important point. So in a Moore state machine, output depends on the current state of the sequential circuit and also external inputs. So in a Moore state machine, output is going to depend upon the current state and also the external input. So in a Moore state machine, output depends on the current state of the sequential circuit and external inputs. So you can see clearly, so these are input and this is output. So output is depending upon the present state and also the external input. So output is going to depend upon the present state and also the input. So it is depending upon two things. So in a Moore state machine, output depends upon the current state of the sequential circuit and also the external inputs. So in a Moore state machine, you can see clearly output is depending upon the state, the current state and also the external input. Whereas in the Moore state machine, output depends on only current or present state of counter. So you can see clearly here for a Moore state machine, so output is depending only on the state, It is independent of the input. You can see clearly it is depending only on the state. So if this is a state means always the output is always equal to 0. If this is a state means output is always equal to 1 irrespective of the input. So we can say clearly, see, for a Moore state machine, output depends only on the current or present state of the counter. So it is depending only on it is only depending upon the current state of the machine. So in a Moore state machine, you can see clearly from this one, it is independent of the input. Whereas here, output is depending upon the current state machine and also the external input, whereas here output is depending only on the current state of the machine. So these things that you always have to keep in mind. So easy way we are writing x by y. X is called as the input and y is called as the output. So finally I can say that in a mirror state machine, output depends upon the current sequential state, current state of the sequential circuit and also external inputs. Whereas in the mirror state machine, output depends only on the current or present state of the counter, and x by y is called as x is input and y is a counter. So this is the mirror type machine. For a mirror type machine, this is the small circuit diagram. You can see clearly this is the S naught. So whenever the input is equal to 0, output is always equal to 0 in the same state. If you give input is equal to 1, it is going to new state then output of 0. Suppose if the input is equal to 0, it is going to be in the same state with output of 1. If you are going to give an input of 1, it is going to go to the new state of S0 with an output of 0. For a mirror type, you can see clearly, suppose S0 is a state. For 0 input, it is going to present in the same state with an output is always equal to 0. Suppose if you are going to give a state of input of 1, it is going to a new state with an output of 1. Whereas if you give an input of 1, it is going to be in the same state with an output of 1. If you give an input of 0, it is going to the whole state with an input with an output of 0. So we can say clearly in a mirror state machine, always whatever the output, it depends upon the current state of the machine and also external input. Whereas here output is depending only on the current state of the machine. So these things that you always have to keep in your mind. So by using mirror state machine to detect the n-bit sequence, we require n states, and the number of flip-flops is always hidden. I have already told you this important point, which is n is smaller is greater than or equal to log capital with a base 2. So this is smaller greater than or equal to log n with a base 2. Where smaller is always an integer number because flip-flops are always like a number, they are purely number. So I have already told you by using mirror state machine to detect the capital bit sequence, we require capital states and the number of flip-flops. I have already told you this important point. The number of flip-flops are to the power of small n greater than or equal to capital N. So therefore, if you apply the log base, if you apply the log base 2 on both sides, we are going to get small n greater than or equal to log n with a base 2. Where n is the number of flip-flops, it's always an integer. Similarly, by using the mirror state machine to detect the capital bit sequence, we require minimum capital N plus 1 states, capital N 1 states. So if you want to find number of flip-flops, same thing, smaller greater than or equal to log of capital N plus 1 with a base 2. So these things that you always have to keep in your mind. So by using mirror state machine to detect the capital N bit sequence, we require capital N states. So the number of flip-flops is to the power of a small n is always greater than or equal to capital N. So if you apply the log base 2 on both sides, small n greater than or equal to log n with a base 2, where n is always an integer. So by using the mirror state machine to detect the capital N bit sequence, we require minimum capital N plus 1 states. So if you want the number of flip-flops, to the power of n is always greater than or equal to capital N plus 1. So if you apply the log base 2 on both sides, small n greater than or equal to log of n plus 1 with a base 2. So these things that you always have to keep in your mind. Accuracy of weighted resistor DSC is very less due to use of different resistors. To overcome this problem, we will study R2R ladder circuit is used. I have already told you accuracy of weighted resistors. Weighted resistance means I have already told you for low resistance, the switch is connected to low resistance is MSB and the switch is connected to high resistance is always LSB. So these things I have already told you, and LSB resistance is equal to the power of small n minus 1 into to the power of 40 to the power of 40 to the power, which is small n minus 1 into MSB resistance. These things I have already told you. So accuracy of weighted resistor DAC is very less due to use of different resistors. To overcome this problem, we will study R2R ladder circuit is used. So I have already told you in the ladders, in the DAC circuits, we are going to study two things which are called as the R2R ladder circuit and also weighted resistors. So out of them, the accuracy of the weighted resistance is very less. So we are going to study the R2R ladder circuit. All these things I have already told you. So accuracy of the weighted resistors DAC is very less when compared to accuracy of the R2R ladder DAC. So accuracy of the weighted resistor DAC is always lesser than the accuracy of the R2R ladder circuit. Now the next one is the number of computers required for a n-bit comparator ADC is to the power of n minus 1. These things I have already told you, to the power of n n is minus 1. So I have already told you the number of computers which are going to require for the n-bit computer type ADC or flash type ADC, which is to the power of n minus 1. Whereas the number of registers are to the power of n. And I have already told you the resolution of the step voltage in the flash type is VR by to the power of n. VR is called the difference voltage by to the power of n. All these things I have already told you. All these concepts I have already told you in the flash type concepts only. The flash type, you can say it is basically a flash type ADC analog to digital converter. All these things I have already told you. So number of computers required for the n-bit comparator type ADC is to the power of n minus 1. Any n-bit weighted resistor digital to analog converter, if LSB resistance is R0, then MSB resistance is, I have already told you, LSB resistance is equal to the power of n minus 1 into MSB resistance. So MSB resistance is equal to LSB resistance by to the power of n minus 1. If R0 is LSB resistance, then MSB resistance is equal to LSB resistance by to the power of n minus 1. So this is the formula that you always have to keep in your mind. So LSB resistance is always equal to the power of n minus 1 into MSB resistance in a weighted resistor DAC. In a n-bit weighted resistor DAC, always, I have already told you, the accuracy of the weighted resistor DAC is always lesser than the accuracy of the R12 ladder circuit. I have already told you. So therefore, if LSB has a resistance of R0, then MSB resistance is equal to LSB resistance by to the power of n minus 1. So the formula that you always have to remember is LSB resistance is equal to the power of n minus 1 into MSB resistance. An astable multivibrator has two quasi-stable states or no stable states. A stable multivibrator means it is not going to have any stable states, always fluctuating from 0 to 1 and 1 to 0. So we can say no stable state or two quasi-stable states. So we can call like this: a stable multivibrator is going to have two quasi-stable states or no stable state, because its output is always fluctuating from 0 to 1 and 1 to 0 on a consequent basis. So we can say there is no stable state, or simply we can say two quasi-stable states. So finally I can say that an astable multivibrator has no stable state or two quasi-stable states. So this is a very important thing that you always have to keep in your mind. So therefore simply we can say that an astable multivibrator has two quasi-stable states or no stable state. So an astable multivibrator has two quasi-stable states or no stable state. So this is the important thing that you always have to keep in your mind. Whereas for a bistable multivibrator, it has two stable states. Whereas for an astable multivibrator, it has no stable states or two quasi-stable states. The number of voltage intervals of an n-bit resolution ADC is the number of voltage intervals of an n-bit resolution ADC converter to the power of n. So this formula that you always have to keep in your mind, which is simply I can say that the number of voltage intervals of an n-bit resolution ADC to be converted analog digital converter is to the power of n. So finally, the number of voltage intervals of an n-bit resolution ADC is converted to the power of n. So this formula you have to always remember. So therefore, the number of voltage intervals of an n-bit resolution ADC is to the power of n. So the number of voltage intervals of an n-bit resolution type ADC is converter is always to the power of n. So the number of voltage intervals of an n-bit resolution type ADC converter is to the power of n. The number of voltage intervals of an n-bit resolution type ADC converter is always to the power of n. The number of voltage intervals of an n-bit resolution type ADC converter is always to the power of n. The number of states possible with n-bit. The number of states possible with n-bit is equal to the power of n. These things I have already told you. So these things are already told you. The number of states possible with n-bit is nothing but to the power of n. So with n-bit flip-flop we are going to get to the power of n states. The number of states used in n-bit Johnson's counter. So the number of bits used in Johnson's counter means we can say it is a Johnson's counter. So Johnson's counter of Johnson's counter is nothing but which is 2n. I have already told you the number of states used in n-bit Johnson's counter is 2n, whereas the number of unused states in n-bit Johnson's counter is to the power of n minus 2n. Whereas for ring counter, the number of states which are used are n, and the number of unused states are to the power of n minus n. These things I have already told you. So therefore, for a n-bit Johnson's counter, the number of used states are 2n, and the number of unused states are to the power of n minus 2n, and the total number of states are to the power of n. So finally I can say that in a for the number of states possible with n bit is equal to the power of n. The number of states used in n bit Johnson's counter is 2n, and the number of unused states in n bit Johnson's counter is to the power of n minus 2n. In a flash type ADC converter, the priority encoder is used for selecting the highest value input. I already told you in a flash type ADC, or simply we can also call as the converter type ADC, it is going to use to the power of n resistors and to the power of n minus 1. Don't miss the minus 1. To the power of n minus 1 number of converters we are going to use, and we are going to use a priority encoder. Priority encoder means I already told you whichever the input is high, the maximum priority is going to give you that corresponding minor output we are going to get. So I already told you for the priority we can say encoder. See for decoder, the decoder means simply I already told you n cross 2n. So encoder means 2 to the power of n cross n. That is the order of this, or we can say for encoder basically this is called as the 2 to the power of n cross n is 2 to the power of n inputs and n outputs. So in a flash type ADC, the priority encoder is used for selecting the highest value input. So whichever is high in highest input means maximum priority, that corresponding output only we are going to get. Weighted resistor in DA converter flash successive approximation dual or AD converters. I already told you weighted resistor. So weighted resistor and R2R. So weighted resistor and R2R ladder, these both are called as the digital to analog converter, whereas the flash type, successive approximation type, dual slope are called as the analog to digital converter. All these things I already told you. Easy to remember is Captain searching first record. So Captain means Siemens we can say counter type ADC. ES means successive approximation type and flash type, and also the dual slope. All these are called as the ADC, not the digital converter, whereas the weighted resistor and the R2R ladder circuit are called as the digital to analog converter. All these things I already explained. And always bandwidth into rise time is always equal to 0.35. So bandwidth into rise time is always equal to constant, which is equal to 0.35. So bandwidth into rise time is always equal to constant, which is equal to 0.35. So bandwidth into rise time is always equal to constant, which is 0.35. And a n-bit modulo to the power of n ripple counter uses JK flip-flops. If the propagation delay of each flip-flop is TPD, the maximum clock frequency, that is, I already told you for n-bit modulo to the power of n ripple counter uses JK flip-flops. If the propagation delay of each flip-flop is TPD, the maximum clock frequency, that is, I already told you here we are going to use the asynchronous ripple counter. Asynchronous ripple counter means I already told you here basically asynchronous ripple counter means the T clock is always greater or equal to n into TPD produced the delay of each flip flop. So therefore the maximum clock frequency is equal to 1 by n into TPD FF. So the clock frequency is less than or equal to 1 by n TPD FF. So maximum clock frequency is equal to 1 by n into TPD FF. So for n-bit modulo to the power of n ripple counter, use JK flip-flops. If the propagation of the each flip-flop is TPD, then the maximum clock frequency, that is, and value to T clock is always greater or equal to n into TPD FF. So F clock is always less than or equal to 1 by n TPD FF. So because F clock is equal to 1 by T clock, so maximum clock frequency is equal to 1 by n into TPD. So raise-around conditions always arise in a asynchronous circuit. I have already told you raise-around condition. So raise-around condition means always the output is always going to change continuously from 0 to 1 and 1 to 0 like a super fast express. So because if you are going to give a feedback for S and R, if you take a feedback, then we are going to get a JK flip-flop, then we are going to get this raise-around condition is possible only in the asynchronous circuits. So JK flip-flop are generally used in shift registers. I have already told you if you are going to shift the data, like example, I already told you serial input, parallel output, serial input, serial output, parallel input, parallel output, and parallel input, parallel output, like parallel input and serial output. All these things we are going to use the shift registers, means we are going to use the JK flip-flop. So JK flip-flop are basically used in the shift registers. And the master slave flip-flop cannot be converted into D flip-flop. Yes, a master slave flip-flop we cannot convert into D flip-flop because master slave flip-flop is a combination of two JK flip-flops. One after the other cascade combination. One is going to give a clock and the other is going to give a note of the clock. So we cannot convert into D flip-flop. Both are different. So master slave flip-flop is a combination of two JK flip-flops. For one we are going to give As the clock is a frequency, either we are going to give neutral of the clock, which we not get, we are going to give. So both are different. So we can say master slave flip flop and D flip flop are different. So we cannot convert master slave flip flop to D flip flop. Race around condition exists in JK flip flop if J is equal to 1, K is equal to 1. I have already told you race around conditions means always the output is always going to fluctuate from 0 to 1 and 1 to 0 continuously. That is called as the race around condition. So because we are taking a feedback from some flip flop, we take a feedback from output, then we are going to get JK flip flop. So when J is equal to 1, K is equal to 1, we are going to get a race around condition is always output is going to get feedback change continuously because of the feedback is present. With regards for SR flip flop, we are not going to get any race around condition. Whenever N is equal to 1, R is equal to 1, but we are going to get a invalid state means always Q and Q bar both are equal. Whether it can be 0, 0 or it can be 1, 1. But because we are going through feedback for SR flip flop, it is called JK flip flop. So now if we give J is equal to 1, K is equal to 1, we are going to get a race around condition means output is always going to get fluctuate from 0 to 1 and 1 to 0 very fast. So by the master slave flip flop, we are going to reduce the speed of this variation. I will discuss about the characteristics of the RTL logic families. So the important characteristics of the RTL logic families, which is it has the high switching speed, it has the pure noise immunity, it has high power dissipation, and also the fan out is only 5. So therefore we can only take outputs. We can only take from a given circuit, we can take only 5 outputs. So this is the important points regarding the characteristics of the RTL logic families. So they have the high switching speed, it has a pure noise immunity and high power dissipation, and the fan out is only 5. Means they can only take 5 wires from the circuit. So fan out is only 5. So this is the thing that you always have to keep in your mind. So the important characteristics of the RTL logic families are it has the high switching speed, poor noise immunity, high power dissipation, and the fan out is only 5. So we can take only 5 outputs from the given circuit. So we can say the characteristics of the RTL logic families are it has a high switching speed, poor noise immunity, and high power dissipation, and the output and the fan output is only 5. So these are the important things regarding the RTL logic families. It has the high switching speed, poor noise immunity, and high power dissipation, and the output power and the fan out is only 5. So these are the important characteristics of the RTL logic families. So it has the high switching speed and the poor noise immunity and the high power dissipation, and the fan out is only 5. So we can say the characteristics of the RTL logic families are it has high switching speed and the poor noise immunity, and you can say high power dissipation, and also it has only fan out is only 5. When number of inverters are odd inside a feedback, then it is going to act like a stable multivibrator. I have already told you, if in a given feedback, if the number of inverters are odd, then it is going to act like a stable multivibrator. But if there are even number of inverters in a feedback, then it is going to act like a bistable multivibrator. So for bistable multivibrator, we have 2 stable states, whereas for unstable multivibrator, there are no stable states, or we can simply call as the 2 quasi-stable states. A shift resistor with the serial output converted to the serial input is going to act like a shift resistor counter. A shift resistor with the serial output connected back to the serial input, it is going to act like a shift resistor counter. So it is going to count the data from, and it can do the up counting, or it can do the down counting, or it can do any counting. So therefore simply we can say a shift resistor with the serial output connected back to the serial input is going to act like a shift resistor counter. So whatever the shift resistor, it is going to act like shift resistor counter, which is going to do the counting. It can be any counting. A synchronous counter has the least delay time. I have already told you a synchronous counter has the very least delay time, whereas asynchronous counter has the highest delay time, because there in the synchronous counter the delay time is only 1 TPDFF, whereas for asynchronous counter the delay time is equal to n times of TPDFF. So that is the reason synchronous counter has the least delay time when compared to asynchronous counter. And synchronous counter with n bit has only the delay time of TPDFF, whereas for asynchronous counter of n bit it is going to have, which is n into TPDFF. Duality converts from positive logic system to neutral logic system and vice versa. I have already told you duality. The duality is going to convert the positive logic circuit to neutral logic circuit, and similarly vice versa, which is neutral logic circuit to positive logic circuit. So I have already told you positive logic means for high voltage we are going to assign logic 1, for low voltage we are going to assign logic 0. Whereas for neutral logic means for high voltage we are going to assign logic 0, and for low voltage we are going to assign logic 1. So this is the points that you always have to keep in your mind. So one full adder means I already told you. So we can design the one full adder with the help of two half adders plus one OR gate. Or simply we can also design with the help of two XOR gates, two AND gates and one OR gate, because see one half adder. So one half adder is going to contain one XOR gate. See, basically one half adder is going to contain one XOR gate and one AND gate. So two half adders means two XOR gates are two AND gates, but there is a one OR gate. So one half adder contains one XOR gate and one AND gate. So two half adders means we are going to contain two XOR gates and two AND gates and plus one OR gate. So this is the thing that you always have to keep in your mind. So one full adder we can design with the help of two half adders plus one OR gate. Similarly, one full adder full adder is going to contain the combination of two half adders plus one OR gate. So one half adder contains one XOR gate and the one AND gate. So two half adders means two XOR gates and two AND gates. So there is another one OR gate. For master slave flip flop, some facts we are going to study here. For master slave flip flop, some facts we are going to study. The toggle frequency is the maximum clock frequency at which the flip flop will toggle reliably. So for master slave flip flop, some facts. The toggle frequency is the maximum clock frequency at which the flip flop will toggle reliably. I have already told you for a master slave flip flop, the toggling, or you can say the amount of toggling at the you can say output of the slave is very. We are going to control the toggling of the speed of the we are going to control. So with the help of this master slave flip flop, so we are going to combine two JK flip flops in a cascade function, and with the clock we are going to give for one we are going to give positive trigger, means for one it is going to give act like a negative trigger. So we are going to control the speed of the QS, or we can say output of the slave. So master is always controlling the slave. So therefore you can say the toggle frequency is the maximum clock frequency at which the flip flop will toggle reliably. So toggle frequency is the maximum clock frequency at which the flip flop will toggle reliably. So here you can see clearly from this circuit, suppose if y is equal to a, b bar, c, then you can write like this, which is a into c into b bar, and you can also write like this, whole complement and again complement, ac b bar, whole complement again complement. So this is nothing but simply we can write here ac whole bar plus b. You can write like this, ac whole bar plus b. So now if you want to implement this one, you can see clearly this is a into c whole bar, and this is the plus b. So again keep a NOR gate here. So you can see there is an AND gate, there is a NOR gate. So we require one AND gate and one NOR gate. So you can see y is equal to a b bar, c is nothing but ac b bar. So we can write like this, ac b bar whole bar whole bar. So therefore this ac bar plus b. So this is nothing but this is basically NAND gate and there is one NOR gate. So therefore NAND gate and NOR gate. So we need one NAND gate and one NOR gate. This output is a into c whole bar. This is b. So ac bar plus b whole bar. So this is the thing that we are going to get. So in order to implement this one, we require one NAND gate and one NOR gate. D flip flop whose Q bar connected to D will act as a frequency divider circuit. Right shift resistor can be used as a frequency divider circuit. I have already told you D flip flop whose Q bar connected to D will act like a frequency divider circuit. Right shift resistor can be used as a frequency divider circuit. See, whenever you take the Q bar as output and if you connect to the feedback as a D, see if you take the feedback from Q bar and if you connect it to D, it is going to act like a Johnson's ring counter. I have already told you this one. So D flip flop whose Q bar connected to D will act as a frequency divider circuit. Plus the output is always going to get changed from 0 to 1, 1 to 0, like all these things it is going to change. So it is basically a frequency divider circuit also. So a D flip flop whose Q bar connected to D will act as a frequency divider circuit. The right shift resistor can be used as a frequency divider circuit because I have already told you whenever you take a feedback from Q bar and if you give to Q, it is going to act like a Johnson's counter. So Johnson's counter, so it is acting like a frequency divider. A synchronous ripple counter can also be used as frequency divider circuit. A synchronous ripple counter can also be used as frequency divider circuit. Yes, I have already told you asynchronous ripple counter. Asynchronous ripple counter means I already told you for all the flip flops we are going to give the same clock at the same instant. Then I already told you for MSB what is the frequency. For MSB frequency I already told you F by mod number. Mod number I already told you. So therefore it is going to act like a frequency divided circuit. These things are already told you. So a synchronous ripple counter can also be used as a frequency divided circuit. So you can see clearly from this K map. Suppose it's a K map like this. Is the F, is the Wx, Yz. So it is a function of Wx, Yz input. The W is the MSB and Z is the LSB. So 0 0 0 1 1 1 1 0 0 0 0 1 1 1 1 0. So now you can see clearly. So now I want to mark the zeros, not the ones. So I want to mark the zeros. So you can see clearly this is the one type of zero. So this is one combination and this is the one combination. So this is the one combination. So now first thing is you have to think like this. So whatever the zeros you have to think they are ones. You have to think they are ones. So then how you are going to write? How you are going to write basically? So this equation is nothing but W into X bar. So this is W into X bar. So W into X bar means W into X bar you are going to get, right? So W into X bar. So W into X bar. So here for this one, so basically listen carefully. For this one, if you group all these zeros, so this is a W, it is a one variable common, and here is one variable common, which is Y bar. So W into Y bar. So W into Y bar. So now for this one, if you take this one, the common terms are here 0 0 is a common means X bar, and here common term is here 0 0 0 means W, Z bar is a common. So here which is basically in this one which is X bar is common and here Z bar is common. So therefore X bar, Z bar and Y W bar. Take the complement of this one. So we are going to get W bar plus Y and X plus Z. So now do the POS form. So product of sum we are going to get F is equal to X plus Z into Y bar plus W bar plus Y. Now you can see clearly. See, I am going to group the zeros. So basically what I am doing is basically I am grouping the zeros. So you can see clearly here I am grouping the zeros. Please I am going to assume whatever this function F I am going to assume as the F bar. So if I am going to assume the F bar means I am going to group in the ones. So therefore this is the grouping zeros is nothing but say for a function F, if I am grouping the zeros means here for F bar we are grouping the ones. So we are writing in terms of the SOP format. So F bar is equal to WY bar plus X bar into Z bar. So this term is nothing but I have already told you which is this is the W into this is called as the Y bar and this is called as the X bar into Z bar. So if I do the again complement of this one, then this SOP is going to become a POS in this format. So F is equal to W bar plus Y into X plus Z. So this is called as the F. So this is called as the F is equal to X plus Z into W bar plus Y. So for a function, see SOP means we are going to group the ones, and for POS means we are grouping the zeros. So you can also do like this. Suppose if you are grouping the zeros, so first write the min term. This is W bar and X bar Z bar. So if you want POS, I can do the complement of this one. So we are going to get W bar plus Y and X plus Z. So now do the product of these two terms. So listen carefully. The first thing is I already told you. First, if you want to write in terms of POS, first group the zeros. So first group the zeros, and you are going to get a certain expression. Write in terms of the SOP format, min term you will write. And now do the complement of that one. So you are going to get the max term. So then do the multiplication of these two things. So this is called as the basically we can say this is called as the POS forms. Listen carefully. So first group the zeros and try to write in terms of min term. Then to the complement of that we are going to get the max term. So now do the product of all the max terms we are going to get the function F. So basically it is a grouping of zeros. If inputs are same across XNOR, then output is always equal to logic 1. I have already told you for XNOR it is also called as equivalent circuit. So for a 2-bit, whenever the inputs are same we are going to get the logic 1. So if inputs are same across XNOR, then output is equal to logic 1. And n input AND gate, and n input AND gate can be replaced by n minus 1 number of 2 input AND gates. Listen carefully. And n input AND gate can be replaced by n minus 1 number of 2 input AND gates. So an n input AND gate we can replace by n minus 1 number of 2 input AND gates. Similarly, to implement a n input NAND gate, we require 4 minus 3 number of 2 input NAND gates. So these are the important things that you always have to keep in your mind. So finally, I can say that an n input AND gate can be replaced by n minus 1 number of 2 input AND gates, whereas an n input NAND gate can be replaced by 2n minus 3 number of 2 input NAND gates. So these are the two things that you always have to keep in your mind. So therefore, an n input AND gate can be replaced by n minus 1 number of 2 input AND gates, whereas basically an n input NAND gate can be replaced by 2n minus 3 number of 2 input NAND gates. So these are the important things that you always have to keep in your mind. So an n input AND gate we can replace by n minus 1 number of 2 input AND gate. Similarly, an n input NAND gate can be replaced by 2n minus 3 number of 2 input NAND gates. So these are the two things that you always have to keep in your mind. So simply I can say that an n input AND gate can be replaced by n minus 1 number of 2 input AND gates. Similarly, an n input NAND gate can be replaced by 2n minus 3 number of 2 input NAND gates. The data input must precede the clock triggering its transition time by some minimum time. The data input must precede the clock triggering its transition time by some minimum time. It is called the setup time. And the data input must remain fixed for a given time after the clock triggering its transition time for a reliable operation. So this is called setup time and this is called as a hold time. So we can say that before the clock edge triggering occurs, always the input has to hold for the given circuit for a small amount of time. That is called setup time. And simply after the clock is arrived, again the input has to remain for a certain amount of time. That is called as a hold up time. If these two are satisfied, then only we can predict the output. Otherwise, we can't predict the output. It will be in the metastable state. So we can say that the data input must precede the clock triggering its transition time with some minimum time. This is called setup time. Similarly, the data input must remain fixed for a given time after the clock triggering its transition time for a reliable operation. So this is called as a hold up time. So if these two are satisfied, then only we are going to get the output as a predicted output. Otherwise, we don't know what is the output. It is called as a metastable state. So the data input must precede the clock triggering its transition time for some minimum time. This is called setup time. Similarly, the data input must remain fixed for a given time after the clock triggering its transition time for reliable operation. So these things I have already told you in our class only. So it is called setup time and this is called as the hold up time. So setup time means the input should come before the clock is triggering occur for a small amount of time. It is called as setup time. And hold up time means the input should be always kept after the even after the clock is appeared, is triggering appeared. Even after the time, a small amount of time, you have to keep the inputs again for you have to remain them for a small amount of time. That is called as the hold up time. So the data input must precede the clock triggering its transition time by some minimum time is called as the setup time, and the data input must remain fixed for a given time after the clock triggering its transition time for reliable operation. If inside the feedback there are n inverters plus buffers and the number of inverters are compulsory odd, then the circuit behaves like a stable multivibrator and the propagation delay of the inverter and buffer is the same, then T is equal to 2n TPD. So 2n TPD is the formula. So listen carefully. If inside the feedback there are n inverters plus buffers, so it's a combination of inverters plus buffers and the number of inverters are compulsory odd, then the circuit behaves as a unstable multivibrator and the propagation delay of the inverter and the buffer is same, then T is equal to 2n TPD. So this is an important formula that you always have to remember. Suppose inside a feedback there are some buffers and also there are some we can say inverters. So if you count the number of inverters, if it is odd, then we can say it is said to be. It is said to be if there are some inverters, then we can say if you count the number of inverters inside the feedback, if it is odd, then we can say it is said to be unstable multivibrator. And the time period is called 2n TPD, where n is the combination of total number of inverters and also the buffers. So therefore, TPD is the particular delay is the same for both buffers and the inverters. So this is the point that you always have to keep in your mind. So what I am trying to tell you, suppose in a given circuit, suppose in the feedback, if it's a in the feedback, if it is as both the combination of inverters and buffers, and if you count the number of inverters, if it is odd, then we can say it is unstable multivibrator. So you are going to get a square wave output. So I want to find what the time period is equal to 2n TPD, where n is the number of so combination of both the inverters and also buffers. And also here TPD is called as the propagation delay is same for both the buffers and also the this one, which is called as the inverters. So this is the important point. Here n is both the combination of inverters and also the buffers, but the number of inverters should be always equal to odd. Then only we are going to get the square wave output, or we can say it is acting like a unstable multivibrator. So if inside the feedback there are n, which is the combination of inverters plus buffers, and the number of inverters are compulsory odd, and the circuit is going to behave like a unstable multivibrator, and the propagation delay of the inverters and buffers are same, which is equal to TPD, then overall time period is equal to 2n TPD, where it is a combination of both the inverters and also buffers, and the number of inverters should be always equal to odd, and the TPD is called as the propagation delay of the buffer and the inverters are same. So you can see clearly the bubbled OR gate is always equal to NAND gate. The bubbled OR gate is always equal to NAND gate because here A and B. So A bar plus B bar is nothing but simply A into B all bar is equal to A bar plus B bar. So both are same. Similarly, bubbled NAND gate is equal to NOR gate because A bar B bar. So A bar into B bar is equal to here AB all A plus B all bar is equal to A bar into B bar. So we can say here bubbled OR gate is equal to NAND gate and the bubbled AND gate is equal to NOR gate. So bubbled, you can see clearly bubbled OR gate is equal to NAND gate and the bubbled AND gate is equal to NOR gate. So listen carefully, bubbled OR gate is equal to NAND gate and the bubbled NAND gate is equal to NOR gate. So static hazard may occur in two-level logic circuit and dynamic hazard may occur in multi-level logic circuit and essential hazard may occur in asynchronous circuit. So this is the important thing that you always have to keep in your mind. A static hazard may occur in the two-level logic circuit, whereas a dynamic hazard may occur in the multi-level logic circuit, whereas the essential hazard can occur in asynchronous circuit. So asynchronous means I already told you the output of one flip-flop is given as a clock to the other flip-flop, it is called as a asynchronous circuit. So these are the important things that you always have to keep in your mind. A static hazard may occur in the two-level logic circuit, whereas a dynamic hazard may occur in the multi-level logic circuit, whereas the essential hazard may occur in asynchronous circuit. So static hazard may occur in the two-level logic circuit, which dynamic hazard may occur in the multi-level logic circuit, whereas the essential hazard may occur in the asynchronous circuit. So static hazard may occur in the two-level logic circuit, whereas dynamic hazard may occur in the multi-level logic circuit, whereas the essential hazard may occur in the asynchronous circuit. See, root 41 with some base B is equal to 5 in a base of 10. So this root 41 will be written in the terms of some base B. Here 5 we have written in the terms of base 10. So if we do the square of this, we are going to get 41 is equal to 25. So 41 is in the terms of base B is equal to 25 in the base of 10. So you can convert this a number in the base B to decimal and you can equate it, then you can find the value of this base B, we can easily figure out. So therefore we can easily convert this a number in the base B to the decimal number with this b to the power of 0 b to the power of 1. So if we do 4 into b to the power of 1 plus 1 into b to the power of 0 is equal to 25. So we can easily get the value of the b. So therefore we can even do the squaring here. So there's a root 41 in terms of base b is equal to 5 in the base 10. So do the squaring on both sides, we are going to get this fashion and you can convert this base b number into decimal number with the help of b to the power of 0, b to the power of 1, and if you can equate and get the value of this base b. See, encoder is always going to convert any other number system to the binary number system. I have already told you encoder is going to convert any other number system to binary number system. So I have already told this important point. So encoder is always going to convert any other number system to binary number system. whereas the decoder is going to convert the binary number system to any other number system. So encoder is going to convert the any other number system to binary number system, whereas the decoder is going to convert the binary number system to any other number system. So decoder is nothing but n cross 2 to the power of n, and here this to the power of n cross n. So this is n cross 2 to the power of n, and this is 2 to the power of n cross n. These things I have already told you. So for a decoder, we are going to get n cross 2 to the power of n. So here it is 2 to the power of n cross n. So NAND gate, NOR gate, A bar plus B, A bar B, MUX, ROM are called as the universal gates. I have already told you NAND gate, NOR gate, A bar B, A B bar, A bar plus B, and A plus B bar, and the MUX and ROM are called as the universal gates. The number of 2 cross 1 MUX needed to implement the 2 to the power of n cross 1 MUX is 2 to the power of n minus 1. I have already told you the number of 2 cross 1 MUX needed to implement the 2 to the power of n cross 1 MUX is nothing but 2 to the power of n minus 1. So 2 to the power of n minus 1 number of 2 cross 1 MUX are needed to implement the 2 to the power of n cross 1 MUX. So in implementing the n cross 1 MUX using p cross n MUX is, I have already told you. So if you want to implement the, say implementing n1 cross MUX using p cross 1 MUX. So we are implementing the n cross 1 MUX using the p cross 1 MUX, means n is greater than p. So therefore now the easy way to do this one, which is m by p plus m by p square plus m by p cube, like that you have to choose the quotient. You have to take on the quotient value. So use this formula only when the last quotient value is 1. So you have to use this formula only when the last quotient value is 1, otherwise you don't have to use this formula. So you have to use this formula only when the last quotient value is 1. Otherwise you don't have to use this formula. So simply we can say implementing n cross 1 MUX using the p cross 1 MUX means n is always greater than p. So therefore simply we can say m by p plus m by p square plus m by p cube. So like that we have to do until we get a quotient value is 1. So this bracket indicates quotient. So try to figure out the quotient and do the summation of all these things, you are going to get the value. So this value is going to indicate this many number of p cross 1 MUX are needed to implement the n cross 1 MUX. So always here in this case n is always greater than p. So you have to use this formula only whenever the last quotient value is 1, otherwise you don't have to use this formula. So this is a formula with some constraint. So I already told you, suppose y is equal to a XOR b XOR c, then we want to write in terms of minterms. I already told you the sigma m, the minterms means summation of all the minterms, which is m of small m of 1, 2, 4, 7. So at these inputs, at these minterms, you are going to get the 1, corresponding 1. So sigma m of 1, 2, 4, 7 means these minterms that you have to add, it is sum of product terms, SOP, sum of product terms. If you are writing in terms of maximum terms means you have to write pi capital M of. So pi capital M is product, pi means product. So pi capital M of the remaining zeros means wherever the zeros are there, you have to write those max terms, you have to write here. See, implementing 1 cross in Vmax using the 1 cross P Vmax. So I already told you here Vmax is nothing but inverse of Mux. So inverse of Mux is nothing but, if you take the mirror image of Mux, you are going to get the Vmax. So if you want to implement the 1 cross in Vmax using 1 cross P Vmax, the same procedure. Here m by p plus m by p square plus m by p cube, like that. And the last, this is called the quotient. So last quotient value should be always equal to 1. Then only this formula is valid. So therefore these are the important points that you always have to keep in your mind. So this formula is also valid whenever the last quotient value is 1. Otherwise you don't have to use this formula. So always m is always greater than p. So therefore implementing the 1 cross m Vmax using the 1 cross p Vmax. So this is the formula m by p plus m by p square plus m by p cube. So these are this bracket indicates the quotient values, and you have to do the summation of these. So last quotient value should be always equal to 1. Then only you have to use this formula. So see, basically Vmax is the mirror image of the Mux. So use this formula only when the last quotient value is 1. So I have already told you. So you have to use this formula only when the last quotient value is 1. Otherwise you don't have to use this formula. So I already told you 1 cross to the power of n Vmax is equal to n cross to the power of n equal to, I already told you here Vmax means only one input, but to the power of n outputs means n select lines. So if you interchange the input and the select lines, you are going to get the decoder, which is n cross to the power of n. N is called as the number of select lines, and to the power of n is called as the number of outputs, and there will be one enable input. So this is called as the, so just interchanging the number of select lines and inputs of a DMUX, you are going to get the decoder. These things I already told you. So decoder remains n cross to the power of n. So encoder remains to the power of n cross n. In order to implement the higher order decoder by using lower order decoder, convert this both to DMUX and by using DMUX formula, find the answer. So in order to implement the higher order decoder by lower order decoder, convert this both to DMUX and by using DMUX formula, find the answer. So if you want to implement a higher order decoder with the help of lower order decoder, then first to simplify in terms of DMUX and then use the DMUX formula which I have already told you. So you are going to get the answer. So in order to implement the higher order decoder by using lower order decoder, first convert this both to DMUX and by using the DMUX formula, find the answer. So they are given, suppose if they are given higher decoder, I want to implement in terms of lower order decoder. So first convert in terms of the corresponding DMUX and then use the formula which I have already told you, the DMUX formula, and try to figure out the value. In SR latch, if the previous state is invalid, then if you give inputs in such a way to get output using memory state, then the outputs can be a 0,1 or 1,0 based on the propagation delays. I already told you in SR latch, if the previous state is invalid, then if you give inputs in such a way to get output using the memory state, then the outputs can be a 0,1 or 1,0 based on the propagation delays. I already told you in SR latch, if you give the invalid state, if you give the invalid, suppose if you are going to get the invalid output, then the next stage if you give an input which is going to give you memory, then the memory will not be the previous output, it will be either 0,1 or 1,0 based on the propagation delays, which device is acting very fast. So we can't predict the output. That is the reason we are not going to use the invalid state. Invalid state means both the states are same. So after invalid state, if you give the memory input, if you give the memory input which corresponds to memory, then it will be never be the previous state. It will be either 0,1 or 1,0 based on which of the device is acting very fast. So in SR latch, if the previous state is invalid, then if you give inputs in such a way to get the outputs in the memory state, then the outputs can be either 0,1 or 1,0 based on the propagation delays. I have already told you setup time is the minimum time to keep the input data before the active edge of clock arrives. I have already told you, so before the clock is coming, you have to keep the input from a given circuit for a small amount of duration, that is called setup time. Setup time is the minimum time to keep the input data before the active edge of clock arrives, and hold time is the minimum time to keep the input data after active edge of the clock arrives. I have already told you, hold time is the minimum time to keep the input data after the active edge of clock arrives. So before the clock arrives means setup time, after the clock arrives means hold time. So for this much amount of time, input should be always kept to the circuit. So therefore this is the meanings of the setup time and the hold time. So therefore setup time is the minimum time to keep the input data before the active edge of clock arrives, and hold time is the minimum time to keep the input data after the active edge of clock arrives. If setup time and the hold up time are not satisfied, then the output is in the metastable state means can't predict. So I have already told you, if setup time and hold time are not satisfied, then whatever the output is in the metastable state means we can't predict it. So then we can say we can't predict the output. It is in the metastable state. So you can say clearly this is called as an XOR gate and this is also XOR gate. So what is this combination? This combination is nothing but simple on XOR gate with of 3 input gates. So you can say, so this combination I already told you, say XOR gate is going to satisfy the associative property. So XOR gate is going to satisfy the associative property. So instead of like this, we can make it a combination of 3. So like this, we can keep this one. So in ripple counter, the flip-flop applied with external clock acts as a always LSB bit. So in a ripple counter, the flip-flop applied with external clock is going to access always LSB bit. I already told you in a ripple counter. So this output of 1 is given as a output of 1 flip-flop is given as a clock for the other. So for that, whichever clock we are going to give. So whichever the clock is directly applied to the flip-flop is called as LSB, and the farthest one is called as the MSB. So this is the point that you always have to keep in your mind. So in a ripple counter, this output of 1 flip-flop is giving a clock for the other flip-flop. So whichever the clock is directly applied to the flip-flop is called as LSB, and the farthest one is called as the MSB. So in ripple counter, the flip-flop applied with external clock is going to access always LSB bit. So no transistor state is present in synchronous counter, whereas the transistor state is present in the asynchronous counter. I already told you, See, transit state is only present in the asynchronous counter, but it is not present in the synchronous counter. I have already told you. So because of this reason only, we are going to use the strobe signal. So for a small amount of time, we are going to keep it as low. For any TPDFF, we are going to keep it as 0 in order not to say this transit state, because people may think that this is also a stable state. That is the reason for a small amount of time, we have to keep the strobe signal as 0. So we can say there is no transit state present in the synchronous counter, but it is only present in the asynchronous counter. So this transit state is present, or we can say unstable state is present only in the asynchronous counter, but it is not present in the synchronous counter. So in asynchronous counter, I have already told you, in asynchronous counter means basically output of one flip flop is given as a clock of other flip flop. Then we can say that here the T clock is always greater or equal to n into TPDFF. So if you apply this one, we are going to get maximum frequency. Maximum clock frequency is equal to 1 by NTPDFF. In asynchronous counter at output, so you can see clearly in asynchronous counter at output, if you see in this fashion 0 1 0 1 0 1 means it is L by 2. Suppose if you see like this 0 0 1 1 0 0 1 1 0 0 1 1 means it is L by 4, because it has sequence of 4. You can see it is only 0 1 0 1 0 1, so L by 2. So it has 1 2 3 4 4 states, you can see common, so it is L by 4. Here you can see 0 1 0 1 0 1, so you can see two states are repeating always 0 1 0 1 0 1, so therefore F by 2. Here 4 states are repeating 0 0 1 1 0 0 1 1, so F by 4. If you go for another, here 8 states are repeating, so 0 0 0 0 1 1 1 1 0 0 0 0 1 1 1 1, so 8 states are repeating, so F by 8. So you can see clearly now here 0 0 0 0 1 0 0 0 0 1, you can see 5 states are repeating, so F by 5. So this is the important thing that you always have to keep in mind. The number of states repeating is equal to clock frequency by that number. So you can see 2 states are repeating, so 2 states are repeating means F by 2. Here 4 states are repeating means F by 4. Here 8 states are repeating means F by 8. Here 5 states are repeating means F by 5. So therefore this is the thing that you always have to keep in your mind for asynchronous counter at the output. So F by 2, F by 4, F by 8 and F by 5. Here 2 states are repeating 0 1 0 1 0 1. Here 4 states are repeating 0 0 1 1 0 0 1 1 0 0 1 1. 8 states are repeating 0 0 0 0 1 1 1 1 0 0 0 0 1 1 1 1. Here 5 states are repeating 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1. I have already told you in the synchronous counter, I have already told you which is T clock is always greater or equal to 1 into TPDFF. So F max is equal to 1 by TPDFF. I have already told you, whereas in the synchronous counter, T clock is always greater or equal to n into TPDFF, whereas here for the synchronous counter, T clock is always greater or equal to TPDFF. So now if you see clearly, this A0 B0, A1 B1, A2 B2, A3 B3, all these are the XOR gates. So if you give again, there is a XNOR, here there is a XNOR. So therefore all these are called as this one. A0 XOR B0, B0, A1 XOR B1, A2 XOR B2, A3 XOR B3. Again you are doing the XOR operation, means I have to keep again XOR and I have to do the complement of that. So this is the important thing that you always have to remember. So this is called as A0 XOR B0, A1 XOR B1, A2 XOR B2, A3 XOR B3. Again you have to do the XOR, again you have to keep the complement. So all complement. So like this you are going to get this one. So A XOR B whole complement, A XOR B whole complement. So R2R ladder sometimes also called as a binary ladder. So I have already told you R2R ladder has the more accuracy when compared to weighted resistor DAC. So R2R ladder sometimes also called as a binary ladder. So in ADC, if the ripple voltage is more than the resolution, then it will go to the next level. I have already told you in ADC, if the ripple voltage is more than the resolution, then it will go to the next level. This is also correct. So in ADC, if the ripple voltage is more than the resolution, then it will go to the next level. The number of comparisons carried out in a n-bit flash type ADC is equal to number of comparators, which is equal to 2 to the power of n minus 1. So the number of comparisons carried out in a n-bit flash type ADC is equal to number of comparators is equal to 2 to the power of n minus 1. So number of comparisons is equal to number of comparators. The number of comparators are nothing but 2 to the power of n minus 1. So therefore simply we can say The number of comparisons carried out in a n-bit flash type ADC is equal to number of comparators. Means I have already shown you in the flash type ADC like a table, the number of comparisons of analog voltage with the values that we know. So it is doing the number of comparisons is equal to number of comparators present. So the number of comparisons carried out in a n-bit flash type ADC is equal to number of comparators present is to the power of n minus 1. A dual slope ADC uses a n-bit counter. When the input signal VA is being integrated, the counter is allowed to count up to a value proportional to VA. I have already told you a dual slope ADC uses a n-bit counter. When the input signal VA is being integrated, the counter is allowed to count up to a value proportional to VA. See, I have already told you in the dual slope ADC, first we are going to connect to the analog voltage and then we are going to connect to the reference voltage. So it is going to get allowed to count up to a value which is proportional to VA. These things I have already told you up to a fixed amount of time t1. So we can say I have already told you as the input voltage varies, the overall time is also going to get varies. As you can see clearly in the I have already told you the dual slope ADC, as the input voltage changes, you can see the peak value changes. If the peak value changes, the overall time is also going to get changes. These things I have already told you. So as the input voltage increases, the overall time increases. If the input voltage decreases, means the overall time decreases. The conversion time decreases. Integrating type ADC is the slowest ADC among all. I have already told you. Integrating type ADC is also called as the dual slope ADC. So it is because we are going to use the integrated op-amp. So we are going to use the integrated op-amp. So that is the result. It's called as the dual slope ADC or integrating type ADC. It is the slowest, means very slow, but it is a very accurate method. So you are going to get the accurate method. I already told you VA is equal to VR into we can it's the ratio of the VA into ratio of the T2 minus T1 by T1. T2 minus T1 is called as the integration time and T1 is called as the first integration time. These things I have already told you, or simply VA is equal to VR into n by 2 to the power of small n. These things I have already told you. So therefore, integration type ADC is also called the dual slope ADC because there we are going to use the integration type op-amp. So it is a very slowest ADC among all the remaining ADCs. So these are the things which are very much important in the digital electronics concepts. So all the important concepts I have already explained in a very detailed manner. So if you like the content of the channel, then please to like, share and subscribe our YouTube channel and don't forget to press the bell icon button. So whenever we upload a new video, the direct notifications comes to your mobile. If any improvements needed in our lectures, then please do comment in the comment section. We will definitely include all those improvements in the comment lectures. Thank you so much for watching this lecture. Keep smiling, take care and bye bye.